In this video, we discuss outlier management. It's one of the most important areas in analytics because of two reasons. First is, it is also an ethical side of managing data. You want to understand that if a data is properly gleaned, if you look into errors and bias and ensure that you have done the best possible job as an analyst to take away errors and bias in the data. After all of that is said and done, an outlier is essentially a specific value in the data set that's different from the others. And it is as true as the data. So at the end of the day, managing outliers becomes an ethical issue on the analyst side, because whether you want to keep the outlier or not depends on whether the outlier helps you or not. And that can be a little dicey. I'll give an example. Imagine that I have to report the average grade of a class to my supervisor, in this case, the dean of the College of Business. And of course, the dean is looking at my average grade as a proxy to how good the class is learning, which basically again turns to how good I am teaching. So imagine that my grades in the class are distributed in such a way that most of the students fall in the 60 to 70 category out of 100. And there is one student who has a perfect score of 100. So clearly, just looking at that lump of data, that one student with a 100 score is way different from the others. And by the basic definition of an outlier, will be an outlier. Should I include that student in my report to the dean? So if that 100 score turns out to be a true outlier, and that's the second part of today's discussion in the video, as to what makes that score a true outlier. Just because it's different from the others, be it high, be it low, doesn't make it an outlier. But if it is a true outlier, should I take it out? Because if I keep it in, I know for a fact that the average value that I'm reporting is gonna be high. And so it makes a good case for myself. If you turn the table and hypothetically assume that most of my students are in the 50 to 60 category in terms of grade, and there is one who has scored a 20 out of 100, that's also an outlier on the other end. Should I report that? Because I know for a fact that the moment I include that in my analysis, it's going to bring my average down and it's going to show poor on me. And so that's where the ethics of reporting lies with outliers, and it becomes a very slippery slope oftentimes. The only thing I want to say is, for anybody who manages data, always have data tell its story. Do not ever allow data to tell your story, because then you are massaging the data. Then you are being unethical with the data set. And so what we'll do as part of this discussion is we start off with the idea of an outlier. So when it comes to a single column of data, an outlier is exactly what we know from the name outlier, something that is different from the rest. So different meaning an extremely high value or an extremely low value compared to most of the others. Okay, so that's the idea of an outlier. But that idea grossly changes when you are talking about multiple columns of data with relationships. So everything that we studied in the context of a scatter plot and correlations and so on and so forth. When you look into data sets that have more than one variable, where you are looking into connectivity or possible relationships or explainability between those variables, in those data sets, the idea of an outlier, in other words, the idea of an outlier in a scatter plot is different from the idea of an outlier in a single column of data. And we will discuss both of those. We'll also talk about identification of a true outlier. Is there an analytical spin to understanding what makes that extreme number, be it a high, be it a low. What makes that extreme number an outlier? And that's where we start the idea of a box plot. Everything that we study in the context of a box plot at the end of the day not only allows us to provide more information than just a couple of summary measures, but the box plot also paves the way to identify a true outlier. And we will end with how to manage outliers, how to understand what outliers mean in the context of the problem, and so on and so forth. So with that, let's quickly go into a basic definition here. It's an important kind of deviation, okay? There are observations that lie outside the overall pattern of a distribution. That's exactly what we talked about. So always look for outliers and try to explain them. And this is where I'm trying to teach you something that I want to take away as part of this video. I did not mention always look for outliers and exclude them. I did not say always look for outliers and delete them and clean the data set. I said always look for outliers and try to explain them. That is the first step of an analyst. Ask yourself, what does this outlier mean in the context? Does it stand a chance of staying in the data set? Is it a valid point of data? Is it still part of the broader diaspora of data? If you cannot explain it, that's when it's a problem. But if you're able to explain it, then maybe it stays. Or the other way around, sometimes you just don't know why it is coming. And so if you don't know why it is coming, what do? You don't just remove it. You can remove something knowing very surely why that outlier happened. But if you only have a hunch, or if you can only say with a certain level of confidence that maybe this is because it happened, maybe is not enough justification to remove the outlier. So sometimes what happens is when you are gathering data, let's say from a survey, when you see a survey response, you can see sometimes a trend in how respondents are responding to a certain question. And depending on how the question was worded, sometimes a respondent makes a mistake. And these are all the biases and errors we talked about. So those are outliers that you can define very easily, why they happened. So you know the exact reason behind those. And if that reason is somehow clouded in bias in the error of judgment, then you can take those out. But if you can't explain them, there is no reason for you to take them out. So here is a quick example. Let's talk about number of states on the y-axis and the percent of state residents that are aged 65 and over. So clearly you see that this group here and this group here are kind of different from the rest of the distribution. And so in essence, what you see here is in Alaska, the percent of state residents who are aged 65 and over are extremely small, between 5 and 6%. Okay. And that's only one state here, which basically tells you that Alaska is primarily demographically with much younger population. It is of no surprise that because of fantastic weathers and conditions that help people with uh, typical old age symptoms, be it breathing, be it something else, close to the sea, Florida oftentimes is a target for retirement planning for most individuals across the country. And so you see an extremely high percent, 18 to 19% of people who are age 65 and over in the state of Florida. So the overall pattern is fairly symmetrical except for two states that clearly do not belong to the main trend. Alaska and Florida have unusual representation of the elderly in their population. So when there is a large gap in the distribution, that is when you see the sign of an outlier. Okay, when there is a gap in the distribution, that's a sign of an outlier. Impact of outliers. So impact of outliers can be something that we discussed in the context of descriptive statistics in the previous video when we were talking about the mean and the median, how the mean is composed of the magnitude of the data points, and it provides equal weight to all the data points, which is why the mean is heavily dependent on an outlier with a high magnitude or a very low magnitude, but which has been considered equally with every other data point. Median, on the other side, stays true to the data. It is centrally placed for a data set that is arranged in an order, and so it is much less dependent on outliers. Okay, so here is an example. So disease X, percent of people dying over time. So this is your percent of people dying over time on the y-axis. And you're talking about years since diagnosis. Okay, so within 7 years of diagnosis, you see most of the data points that are here. And so the way you want to read this chart is that within 1 year of diagnosis, 5% of people die. Okay, between 1 and 2 years of diagnosis, 10% people die, or another 5% people die. Okay, so between 2 years of analysis, 10% of people die. Okay, within 4 years of analysis, 1/4 of the population dies. Okay, and so that's how you would want to look into it. In fact, more than that, between 3 and 4 years of diagnosis, 25% of the population dies. But you look at this outlier, which is where it says about 2% people die after 13 to 14 years of diagnosis. So they kind of stay long. So that's an outlier in its true sense. So what's happening here is without outliers, your overall X is 3.4. Okay, so that's your 3.4. With the outliers, it turns out to be 4.2. It kind of moves one full segment in terms of number of years of diagnosis, and that's a significant distance to travel. So the mean is pulled to the right by a lot due to the outliers from 3.4 to 4.2. The median gets pulled only slightly from 3.4 to 3.6. So median is not as much affected by outliers. So this is where the idea of quartiles, the interquartile range, and what we define as a 5-number summary comes. And let's take a quick look into the 5-number summary in the way we can depict this. So if you have data, let's say for 25 points, okay, and because there are 25 numbers in the data set, if you recall the way we discussed the creation of a median, because it's an odd number, the median is essentially that odd number plus 1 over 2, and that's the position. So 25 plus 1 over 2 is 26 over 2, which is 13, and the 13th position gives you the median. Now, if you look at all the data points that is above the median, excluding the median, the center point or the median of all of those data points above the median and excluding the median is also what is your first quartile. And so as you could see, there are 12 data points here, and because it is even, both the 6th and the 7th position together correspond to the central location. And so you look at their corresponding values, and the average of those values gives you the first quartile or the 2.2 value. The same exact thing happens for the third quartile or the 75th percentile. Okay, so the first quartile is also the 25th percentile. The median is your 50th percentile. The third quartile is your 75th percentile. And so here also, because if you leave the median aside, you have an even number here. So there are 2 central locations, and you take the average of the values corresponding to those 2 central locations, and that gives you your third quartile of 4.35. So it basically means that the first quartile has 25% of the data at or below it. So it is the median of the lower half of the sorted data, and lower half meaning when you're going from ascending to descending the lower half, excluding the median. The third quartile in the same way has 75% of the data at or below it. Okay, so um, this is 25%, this is 75% that is below that value. Okay, and this is excluding the median. Okay, so that's how the quartiles are captured. The idea of an IQR, and we will come back to the IQR concept later on. IQR stands for interquartile range. So if you look at the minimum value here and the maximum value here, so that distance is overall your range. Your IQR is the distance between your 75th percentile and 25th percentile, which is your distance between the first and the third quartile. So this is your Q3 minus Q1, which is 4.35 minus 2.2, which is 2.15. We will talk about the significance of IQR in just a few minutes. The IQR basically holds the fort for utilizing a 5-number summary to identify a true outlier. And we'll talk about that in much more detail in the next few slides. But that's basically what the IQR does. It is the range between the first and the third quartile. So when you think about something called a box plot, it takes advantage of those 5 numbers. Okay, so in essence, you are looking at the smallest or the minimum number, okay, which is showcased here. You take the first quartile, so you are going up, okay? So from minimum to maximum, that's the direction you are going. You're looking at the first quartile, which is 2.2, and that is showcased in that line here. You have the median, which is the central line that is showing up here. You have the third quartile that shows up in the other end of what we define as a box. Okay, so this is your box. The box includes your interquartile range, if you will. So this is your Q3, this is your Q1, this is your median. And then of course your largest value or your max shows up here. So between the 2 quartiles, the median, the max and the min, those are your 5 numbers. And you can summarize those 5 numbers using what we call a box and whisker plot, where this part is your box and these two guys are your whiskers. Okay, so that's your box and whisker plot. The fundamental advantage of this plot is it provides you a lot of bang for the buck, if you will. So in a simple figure such as this one, it not only provides you 5 broad summary measures, the median, the 2 quartiles, as well as the maximum and the minimum value, it also depicts for you the true nature of how the data is dispersed. In other words, when you look at the data set here, it almost feels that it's equally distributed because you're looking by positions here. This is the middle position. This is the central position of the upper half of the data set on top of the mean. This is the central position of the lower half of the data set below the median. Okay, so these all look very symmetric. It doesn't have to be that way in a box plot, because in a box plot, you are plotting the actual variable, how the variable performs in its positions against its actual measure, which is years until death. Okay, so number of years you survive because of a certain disease till you die. And so those numbers are the actual magnitude numbers which are being plotted here on the y-axis. And it's the positional aspect compared to the actual magnitude that provides you a much clearer picture of how the data behaves, how the data is dispersed, what it means to have a minimum value in the context of the measure, what it means to have a maximum value in the context of a measure. Where is the median in relation to the first and the third quartiles? Is the median tilted towards any one of the others? Which basically then tells you that on the other end, you would have some outliers, some extreme values that is pulling the mean or the whisker towards a certain end. So all of that can be accomplished by something as simple as a box plot. And especially when you are comparing disease 1 and disease 2, you are comparing multiple diseases and their respective box plots, it provides a true apples and apples comparison across multiple categorical variables. And we touched base on this very little when we talked about our very first video on visualizing categorical variables. So this is what we are talking about here. So when you are comparing box plots for a, let's say, a normal distribution, which is a very symmetric distribution versus a right skewed distribution. And when you talk about right skewed or left skewed in this format, you're always saying that right skewed meaning you have more values on the right side of it, which is why the mean is on the right side of the median value. This is your median value. The box plot always gives you the median. And so for the multiple myeloma as a disease, as you can see that it is severely skewed to the right as opposed to disease X, which is much more symmetrical. So before even looking into anything else, just by looking at those box plots, you can say that, yes, just by comparing them, they are playing within very similar fields when it comes to the measure of number of years that somebody would survive until death. But data-wise, the multiple myeloma data set has much higher variability. The dispersion or the spread is much more higher compared to the disease X data. The disease X data has symmetry around the median. Here the median is to the left side, which basically means the data is skewed on this direction, and you would want to see multiple large data points to the right end. And that is what is showcased in the distribution or the bar chart, if you will, as compared to the disease X bar chart, which is more or less symmetrical. Okay, so that kind of gives you the broad overview. Now, if you look into each and every of those 5 numbers, it actually tells you a story. So if you look at the first one, okay, so this is your minimum value. Okay, so minimum value meaning at the bare minimum, your death will happen within 1 year for disease X. At the bare minimum, for multiple myeloma, your death will happen even earlier. But on an average, from a 30,000 foot view, you can basically say that one has the capability of dying from either of these diseases within 1 year, because that's where those minimum values are. Now, if you look at the first quartile, okay, which is the 25% for both of these diseases, they tell a little bit of a different story. So the Q1 data for disease X is at the 2-year mark. The Q1 data for multiple myeloma is at the 1-year mark, which basically tells you that a quarter of the individuals in the data set would die of disease X in 2 years, but it would only take them 1 year to die of multiple myeloma. When you talk about the median, okay, that is almost half the population, because that is the true nature of the median. It takes the entire data set and really divides it into two parts. And so you can very well say that half the data set would die of disease X in 3.5 years, and um, half the data set would die of multiple myeloma of um, in 2.5 years, let's say. So they're kind of close. If you're looking into half the population or half the data set, you can make a close connection, which is why these data sets by face value are quite close together. Um, when you look at the um, Q3, okay, or the um, third quartile, or the 75 percentile, you're essentially saying that 3/4 of them are of the data set of individuals would die within 4.5 years, and they are eerily similar for both the diseases, right? Um, but the other side of the whisker, which is the max, kind of tells a very different story. So according to this specific data set, um, disease X will kill almost everybody by 6 years, within 6 years. But patients from multiple myeloma can live longer, up to 14 years in certain situations. And so that's where a lot of your aberrations are, a lot of your outliers are. But everything that we have talked about so far is a tremendous amount of information, even though it is a high level view, but there's a lot to be able to talk about from something as simple as the box plot. And let's talk about this in the context, in different contexts, and hopefully it will make some more sense into what we have been working on so far. So let me share my screen for the Excel file with you guys. Okay, so here is an Excel file of a data set that we had visited as part of our first face-to-face meeting on August 25th, which was the home prices data set. If you recall, we talked about how home prices as a um, Y variable or response variable here um, can be explained as a function of the characteristics of the house, which includes bedrooms, bathrooms, square footage, brick or no brick, as well as by virtue of the location of the house, which is where neighborhoods, offers, and so on and so forth come in. Okay, so imagine that I am trying to understand how the pricing of brick houses and non-brick houses differ. And in the same way we looked into these two diseases, box plots are a fantastic way to try and understand the pricing of homes, irrespective of their neighborhoods, for brick houses versus non-brick houses. Now this is Excel, this is no cool software. So we need to design a little bit of this work to fit the needs of Excel before actually we can decide the box plot. In a software like R, as we'll see in a few minutes, just by dumping this data, R will be able to capture the box plot directly. In Excel, I have to train the data so that I can capture the box plot accordingly. So what I'll do is I'll create a couple of columns, one column with homes pricing for those that are brick houses, another column for homes pricing that are with non-brick houses. Okay, and so the first thing I'll do is I'll create a new sheet, and let me rename this sheet as brick versus non-brick. Okay, and then I go to data, and as you can see, the brick houses have been coded as a no versus a yes, which is categorical data. So I'll go under the home ribbon, and while I have my cursor on the column E, specifically on the label to the column, which is brick. Under the home ribbon, if I go under sort and filter, I can actually use the filter drop down from here. It kind of allows you to filter across all of the other variables as well. But now I have a drop down setup for bricks, which actually is more sensible because of its categorical nature. There are only two categories, no and yes. Okay, so I'll deselect them all, and let's say we are choosing only the specific data points in this data set that are yes to bricks, which basically means they're brick houses. If I choose yes, then only the brick houses are showcased here. Okay, so what I'll do is I'll essentially take all of those values, the prices, if you will, of the brick houses. Okay, and I'll copy them. And if I go under the brick versus non-brick tab that I have created, I'll create a new level that says brick price. Okay, and I'll just paste those values. So whatever I have chosen here, I copy those, and under the brick price, I paste them. So all of those um, values that you see are specific to brick houses only. Okay, I'll create a similar column called non-brick price. Okay, and I'll go back to my data, and this time in my filter, instead of the yes, I'll choose the no. So non-brick, and when I hit OK, it chooses only the houses that have no bricks. And I'm going to again choose the data set. Okay, and as you can see, there are so many more non-brick houses than there are brick houses, right? So I'm going to choose them, and I'm going to copy them, and going into this other folder, other tab under non-brick price, I'm going to paste them. Okay, so as you can see, I have many more non-brick houses than I have brick houses, and that's okay. The data is what it is. Okay, so the question therefore is, can I now use both of these columns and create a chart that is also a box plot in Excel? And the answer is yes. Since 2016, Excel has actually built the box plot as one of its charts. So I go to insert, I go to recommended charts, and by default, it does not recommend any of box plots for me. Okay, it goes into more of a scatter and stuff like that. It's trying to see if there is any relationship between brick prices and non-brick prices, because they're continuous variables. By default, it chooses a scatter. There is really no connection here, so it does not make sense. What you want to do is, right next to the recommended charts, you'll see something called all charts. You click on that, and under all charts on your left, and if you recall, we used this all charts option also when we tried to create a secondary axis. When we were doing the line plots, we chose the combo here, right? So under all charts, there is something called a box and whisker. That's what exactly we were talking about. And it looks something like this. You hit OK, and your chart is created. Okay, you can make this chart a little bit bigger just to make sure that you can explain the chart. And then the rest of the process is exactly the similar to what we did in the other chart creation processes, chart elements. Okay, so you have access, you want to provide access titles, okay, so that people understand what these are. Um, you want to provide a legend that allows people to realize, um, and instead of top, I can choose bottom, and that allows me to um, understand which one of these is non-brick, which one of these is brick, okay? And that's basically it. So now I can go into the chart title, and um, I can write this box plot for brick versus non-brick pricing. Okay, so here um, all you do is brick versus non-brick, and here all you do is pricing. So now your box plot is ready, but it's also important to get an overview of the box plot, okay? So just on face value, you can already say that your brick homes seem to be costlier than non-brick homes, just on face value, because this entire box and whisker plot is kind of moved up compared to this entirety of the non-brick houses, okay? Um, so overall, the brick houses are much higher cost than the non-brick houses according to this data set. Okay, are they statistically different? That a statistical test will reveal. These are not statistical tests. These are visualizations. The other thing that you can also say is for the brick houses, as you can see, this median line is kind of center to both the quartiles, and the brick house data is a lot more symmetrical than the non-brick house data. There are less outliers here. There is less spread in the brick house data set. There is a lot more spread in the non-brick house data set because as you can see, the median is heavily moved towards the first quartile. And that will in turn dictate that there are quite a few higher values for the non-brick house pricing, which is interesting because now if you look into the maximum value for the non-brick houses, that pretty much exceeds the value for 3/4 of brick houses. 3/4 of brick houses fall within the 170,000 category, and the maximum value of a non-brick house is close to, let's say, a 180,000. And so those are all um, specific ways for you to understand where the non-brick houses are gaining high price, and this is where probably the neighborhood could be another way to look into the data set in terms of whether the non-brick houses in certain neighborhoods are priced higher than the brick houses or not. Okay, so all of that jazz can be done in the context of um, visualization. And when we start talking about Tableau from a visualization standpoint, you will see that in Tableau, we do the same exact thing. We can define certain variables to look like they are categorical variables, even though they are numeric, like neighborhood. And in Tableau, that would then allow us to group the data further, not only by bricks versus non-bricks, but also by um, each neighborhood, and looking into bricks versus non-bricks in each of the neighborhoods. And um, we will look into all of that when we discuss Tableau in our next synchronous meeting. And we will probably go back to this same exercise to understand it in a different sense. But This is the essence of understanding a box and whisker plot. Okay, so if you look at the minimum value, um, if you look at that price range, which is, let's say, $70,000, that $70,000 house is probably a non-brick house. It's not a brick house. Now, the $110,000 house is possibly a brick house, but also a quarter of the population or quarter of the data set would um, uh, with a non-brick house would fall within that same price range. So a quarter of the data set that are non-brick houses also falls in that same price range as what a brick house uh, possibility would be for the 110,000. And then as you move up, half of the data set for non-brick houses would be in that 117,000 price range, whereas half of the data set for the brick houses would be in the 147,000 price range. So you can already see that brick houses are much more costlier, and that's what we talk about in the context of outliers. So now let's see how we can put this in a broader context, especially when it comes to R. Let's see how R works with this data set. So let's look into how the same data set can be used in R to create a box plot. And of course, you will find that it's so much of an easier option, especially given that R is a defined statistical software that can directly plug and play with the categoricals and the groups within the categories behind the scenes. You don't have to redefine them into multiple columns for you to create the chart. So we go under data and we go to import data from an Excel file, and let's call that home prices. Okay, and then it's going to ask me which data set I want to open, and I'm going to open the dataset 1. And as you just saw, I had 2 tabs in the dataset. This is the very same discussion that we were having in the other video. The brick versus non-brick is the Excel version of drawing a box plot. So I'm going to use the data table, okay? And so you'll see that the dataset has 128 rows and 8 columns. I can view the dataset, and it actually gives me everything that I need here, okay, the original dataset. So this is very easy here. Under graphs, I go into box plot, okay, and I'm going to use price as my variable, but I'm going to plot the price by groups, and I'm going to use brick as my group. And I hit OK, and your box plot is created, the same exact box plot. It just looks different because in the Excel one, the brick came first and the non-brick came second. In this way, the non-brick, the no comes first and the yes comes next. So this is a brick house box plot. This is a non-brick house box plot. So this kind of tells you the same exact story that we have discussed so far in the context of Excel. The same idea. Box plot reveals a lot more than what a typical summary measure would reveal. So with that, let's get back to our PowerPoint slide. So, and this is why we were talking about box plot, because the box plot allows you to identify the true outliers. So if a number is different from the others, it's a suspected outlier. So outliers are troublesome data points. It's important to be able to identify them. So one way to raise the flag for a suspected outlier is to compare the distance from the suspicious data point to the nearest quartile. So if it is a very high value, then you are going to compare that to the Q3 or the third quartile. If it's a very low value, you're going to compare that to the first quartile or Q1. And then you look at that distance, how far that specific outlier is to any one of those quartiles, depending on where that position is, which one is nearest. And then you log that distance and you compare that to the interquartile range. Specifically, you compute 1.5 times the size of the interquartile range. And you say, as long as the distance of that outlier to the nearest quartile is less than 1.5 times the interquartile range, you are fine. That outlier is not a true outlier. However, if the distance of that specific outlier point to the nearest quartile becomes more than 1.5 times the IQR, now you have a problem. Now you have a true outlier. So here is an example, and this is from the real data from the disease X, and this is an important one to look at because I will explain how the box plot representation is done based off of if there is a true outlier or not. So let's look into the setup first. We already have looked into how to design the box plot. You have the 5 numbers, the 0.6, the 2.2, which is the first quartile. You have the median 3.4. You have the third quartile 4.35. And you have something that we have defined here as the maximum value. Unfortunately, you see that the maximum value is not necessarily that point of 6.1, but it's the point of 7.9, right? So what really changed? Or can you consider this as an outlier? That's the first question. So the first thing that you do here is you calculate the interquartile range. Okay, so we talked about this before. 4.35 minus 2.2 is 2.15. Then you take the distance of that specific outlier point or a suspected outlier to the nearest quartile. In this case, because it was a very high value, you look at the nearest quartile being the third quartile. You check that distance. It turns out to be 7.9, which is the value of the specific suspected outlier point, minus 4.35, which is the value of the third quartile, which is 3.55. That is the distance, how far that suspected point is from the nearest quartile. Now, your individual number 25 has a value of 7.9 years. In other words, this person dies 7.9 years after the detection of the disease. So an extreme high outlier. This is 3.55 years above the third quartile, which is more than 3.225 years. And where does 3.225 come from? It is the 1.5 times IQR, which is 1.5 times IQR, and your IQR is 2.15. So if you do 1.5 times the 2.15, that's your 3.225. That's your 1.5 times IQR. That's your IQR rule for detecting outliers, because this distance of the outlier point from the nearest quartile is higher than the 1.5 times IQR. This individual is indeed a true outlier. So what happens is, if at any point of time you have one of those true outliers out there, the box plot will not report that true outlier. The box plot will report the whisker as if it is 1.5 times the IQR only. Okay, and that is all it will do. It will only add 1.5 times the IQR to the nearest quartile. And that will be what the whisker point would show. And you have to understand that it will never show this as a whisker point just because it's the maximum value, because it's not part of what the original data should show. So that's the value of a box plot. It right away tells you if the data is a true outlier, it stays within IQR. Then everything is fine. If the data is a true outlier, then there is no point of keeping that data in the representation. And the box plot does not represent that outlier in its whisker and boxes. So that's a very important way to understand the trueness of an outlier, especially when it comes to columns of data. And this can be applied even to data sets with multiple columns of data for which you're looking into relationships. But for each of those specific columns, this rule still applies. When it comes to outliers in data with relationships, the idea is a little different. Okay, so far everything that we have discussed is around the magnitude of the data. If the data has a very high magnitude compared to the others or a very low magnitude compared to the others, if it is different from the rest, it's an outlier. From a relationship standpoint, you would want to say that this guy is also different from the rest. But it's really not an outlier because in the relationship context, the outlier is sought from a relationship standpoint. This still matches the overall dynamics of the relationships. If your X increases, your Y also increases. And so this is just a higher value of both X and Y that intersects at that plotting point. That doesn't make this an outlier. They are still on that same plane. However, this guy here is different because you would normally have wanted to find this guy somewhere here. Then that would have followed the rest of the relationship process. But suddenly for that high a value of the X, the Y value is not high enough. And that's where it is an anomaly from the typical expectation of the data set, of how the data set should behave in its association. So outliers are points that fall outside of the overall pattern of the relationship in scatter plots. So this makes it an outlier. This is not an outlier. This is not an outlier. It's part of the overall relationship. So on that same note, number of beers, blood alcohol content, you are talking about which one is an outlier, which one is an outlier. That point here is again following the pattern. That specific female probably just has a lot of capacity to drink a lot, but at the same time, the blood alcohol level is also increasing steadily. So it is nothing different from the rest. The rest of them have drank less and hence their blood alcohol level has also been low. So it's nothing different. This one is a different scenario. It's a different story because this female really is a honcho, as I say. So in the social peer group, this person is well respected because they can drink a lot, but somehow can keep their steadiness and have a much reduced value of blood alcohol content registered in their blood as opposed to where it should lie. So under these circumstances, this particular individual should have been somewhere here corresponding to the rest of the crowd and the nature of the association. Instead, it stops short of this point. Okay, so that is a clear outlier. So as I just mentioned, the upper right hand point here is not an outlier of the relationship. It is what you would expect for this many beards given the linear relationship between beards and blood alcohol. This point is not in line with the other, so it is an outlier in the relationship. There has to be a difference between defining outliers and influential points. Okay, outlier is an observation that lies outside the overall pattern of observations. Influential individual is an observation that markedly changes the regression if removed. That is often an outlier on the x-axis. Okay, so child number 18 is essentially different from the rest of the children in the sense that that specific child says its first words at 42 months. So naturally, its adaptive score is also low, but it just is an outlier across that specific axis, but not an outlier in the relationship. It still follows that same part. As the faster you start saying, the higher your score is. And so as your age increases, in terms of saying your first word, your score also decreases. So it follows that same pattern. So child 18 is not necessarily an outlier. Um, this child who started saying its first words at, let's say, 19 months should have been in this range of the adaptive score. Turns out to be a much higher adaptive score. Not sure what's going on there, but that becomes an outlier. This one is not an outlier. So that's basically what is being talked about. Child 19 is an outlier of the relationship because it's way off. Child 18 is only an outlier in the X direction and thus might be an influential point. On that same note, in this case, this female is truly an outlier because it's an outlier of the relationship process. This female here is an influential point. This female will change your regression definition. It will change the overall mean of the number of beards by female just because of its influential point or the influence that it has over the rest of the females. So this again brings us to the example that we studied earlier when it comes to scatter plots, right? So number of beards, blood alcohol content, irrespective of males and females. So that is where your direction is headed. As you consume more beer, your blood alcohol content should also increase. So this guy is very much within that domain. It is an influential point in the number of beers, but it has consumed, this specific person has consumed about 9 bottles of beer. What do you expect? You of course expect its blood alcohol content to also be high. So this is under no circumstance an outlier. Now, if I give you a certain person here and a certain person here, these are outside of the typical patterns of relationships that we have established for the scatter. That makes them outliers. And you can tell very interesting stories. Let's look at this person. We talked about this in the context of females earlier. Somebody who had 7.5 bottles of beer and still registered what? Only a 0.02 blood alcohol level. That person is a honcho, extremely well revered by peers in their social circles. Okay, um, you have you seem to have a lot more capability to drink without getting drunk, and so that is actually a good thing in certain social circles, especially when you are in school, in the university, and so on and so forth. What about this poor one? Only 2.5 bottles, and zoop, the blood alcohol level has increased massively. And there can be other biological factors, but just looking into those two forms, this person is going to make a fool. These are the people who crawl at ISU's homecoming after 2 or 3 bottles. And that is not necessarily a good thing. Okay, so that kind of explains those outliers in some form. This is that specific point within the relationship that explains if 3 bottles of beer are consumed, your blood alcohol content is 0.07. So we'll end with this quick example. Let's talk about IQ score and grade point average. Okay, if I give you a data set, a scatter plot such as this one, and if I ask you describe in words what this plot shows, in essence, all you can say is this plot tries to explain the relationship between IQ scores and grade point average, specifically if IQ scores are capable of explaining grade point averages. And then if you go deeper into it, you look into describing the direction, shape, and strength. Are there outliers? And so very broadly, that is your band that you are looking at. So the direction is positive. So Overall, as your IQ score increases, your GPA is expected to increase. That's basically what you can hypothesize. The shape, there is a level of linearity to it. Um, the strength of it, I don't know. I can't call it a very high strength. I can't call it very weak either. I'll probably go into a zero point 0.6. And if I had the exact data sets with me, I would run the correlation and I would say that the correlation is close to a zero point 0.6, which basically means that the explainability, as we discussed, is about 36%, which kind of makes sense because IQ score can only take you so far. There are so many other factors that impact grade point average. And then the fun part begins. If you look into this person and this person, what's the deal with these people? Okay. And there are multiple ways to look into it. Somebody with a low IQ score, how does that person get a high GPA? Now, if you want to address that from a negativity standpoint, you can say, well, this person just got lucky in an exam in multiple choice questions. This person chose all answers as A out of the 5 options. And luckily, 80% of the answers were A, and so this person got a high grade, and therefore the GPA improved. I've seen that happen in many circumstances. This person may have cheated, may have copied from somebody else's work, and so irrespective of that, um, uh, even if the person has a low IQ score, the person has a high GPA because the person has been unethical or lucky. That's a negative way of looking into it. I'll provide a more positive spin to it because that's what I believe in. And that is common to both of these processes. In the war between effort and IQ, effort will trump IQ any day. And I say this and I live it for a living. And I say this to all my students. You can have a lot of IQ, you can have a lot of capability and talent takes you nowhere if you don't put the effort. So this student may have a low IQ, may take less time to grasp something, but it's highly possible the student has put in the effort, put in many, many hours of study to up their GPA and has studied a lot more than the others. Probably that is not something that's taken into the model in the very first place, which is why you see such a low explainability of just IQ to GPA. There are so many other factors, the amount of time you put into the materials and so on and so forth. In this case, probably that is the reason why this person's GPA is so high. And I'll say the same thing or the same reason for this person. This person has a very high IQ score, and the person thought, yes, I can beat it just with my talent. Without putting in an effort, that person's GPA suffered. And so you can always try and explain some of these outliers, but that doesn't mean you should not keep them in your data set. Only when you cannot explain an outlier is when you can start thinking, what's going on here? Okay. As long as you can explain the outlier of what may have happened, then you can probably try and take it out, because in this specific example, you are only comparing 2 variables. And so just comparing these 2 variables, these 2 points are clearly outliers. And that's when you make the decision whether you want to take that outlier out or not. If you cannot explain the outlier, that outlier stays. In this context, as I said, there are multiple ways to explain it. But it's also a fascinating area with outliers because it allows you to deep dive into the data to try and understand how the data is behaving.